To be honest with you, it doesn't get much more real world than this. This is kind of one of those things that in math, like if you understand it, it's just so cool to like be able to make connections between this and how money works, or how bacteria replicate, viruses, blood alcohol level. All this kind of stuff is based on exponential functions, like exponential growth, where things duplicate or triplicate, or whatever words you want to use, or exponential decay. Like if I have this particular element from the periodic table in this quantity, and I know that it halves itself over time, like how long will it take to decay into something else? And those sorts of things with carbon dating let scientists predict things like the age of the Earth and everything. So it's just kind of cool stuff. Now, in the past, this will be in red, so you just don't have to worry about it, but you would have had an equation like y equals x to the power of 4. But notice where your variable is hidden. Your variable is actually the base of the exponent. And what is going to make this way more challenging than stuff that you've done before is that the variable x is now located as the exponent. So it's not the base anymore. So just be aware of that, and I'm calling your attention to that so that it's more clear as we move forward in this chapter. Now, this exponential function can be described where a is greater than 0. And I'll just touch on this quickly. But if it had to be greater than 0, it can't be a negative number. So we won't be like doing negative 1/2 of something to the power of x or anything yet. But if it's greater than 0, that doesn't mean it can't be a fraction, because 1/2 is greater than 0. But if I take 1/2 and I square it, I get a 4th, which is a smaller number. But if I take 2 and I square it, I get a 4, which is a larger number. And also notice that a does not equal 1. Well, let's find out why that matters. If 1 is squared, it's 1. If 1 is taken to the power of 5, it's 1. And really that wouldn't be any growth at all. It would just be something staying the exact same. So 1 times 1 times 1 times 1 is never going to change. Now, just like with earlier parts of this chapter when you did graphs over quadratic functions, you're now doing graphs of exponential functions. So graphs are the nice lead-in way to better understand this. So graph y is 4 to the power of x, and then later use the graph to approximate the value of 4 to the power of 1.8. And notice that this is obviously a decimal, and so it's close to 2, so I assume that's what we're doing. As with what we did before, we set up a table of x and y. And optionally, I'm going to include a middle column. And I'm going to try my best to write this consistently in red. So I guess maybe go ahead and do this. It's your call. But for my values of x, I'm going to choose -2, -1, 0, 1, 2. And we'll take this to 3. So that what this means is that I have 4 to the power of -2. If I had more stuff going on up here, I'd probably keep it in parentheses, but it's just a single value. 4 to the power of -1, 4 to the 0th power, 4 to the 1st, 4 squared, 4 cubed. It's nice to set up a table with this in-between chunk for when you have way more things going on and you want to figure this out. Now, from an earlier section, you may or may not recall that anything to a negative power, like a to the power of m, can be rewritten as 1 over a to the negative m. I think sometimes they use n as well. And the same can be said for anything starting with a negative. Like where we have a to the negative n, I can do 1 over a to the n. So basically, what I'm showing you is that 4 to the -2nd power is really the same as 1 over 4 squared, which would be 1 over 16. 4 to the -1st would be the same as 1 over 4, which would be 1/4. Anything to the 0 power is always 1. 4 to the 1st is 4, 4 squared is 16, 4 cubed is 64. And if you wanted to ever check these fractions things, this whole number parts are more comfortable, You can go in reverse and be like, well, divided by 4 does give me 16, divided by 4 gives me 4, divided by 4 gives me 1, a fourth of that, a fourth of that. So by working my way backwards, it helps me to better lock in these ideas. I'm going to use the word elusive. Something that is elusive is a little bit out of reach, something kind of hard to find, catch, or achieve. So I would call some of this a little bit elusive. So I don't rush through this stuff and definitely feel more comfortable. Now, are we told to find the exact value of 4 to the power of 1.8? No. But we are told to approximate, so our graph might need to be a little bit more accurate than some of what we're used to. Planning ahead. I definitely have a couple negative values. I definitely have a couple positive values for x. So maybe I'd like this to be symmetrical about all quadrants. But then I take a closer look and I realize that my y values in this case have not been positive. And because of that, I really have no interest in any negative values for y. We'll show the x-axis. I'm turning my paper, or in this case iPad, to rotate it so that I can more neatly draw that. You should be getting a ruler out for these. This should be neat and not sketched. -2, -1. Look at my graph. I think it's pretty close to being symmetrical on the left and right sides. And I don't think I need to graph all the way up to 64, but it might be helpful to have tick marks all the way to something like 15. And I choose 15 because I can take thirds of 15 at increments of 5. And then if those are equally spaced, I can get pretty accurate on paper. And if my iPad looks this neat, then your paper, I think, reasonably can be better than mine. Now, back to the value at -2/16. Well, that's crazy close to the x-axis, but not on the x-axis. -1 1/4, well, that's a fourth of that value. I mean, that's still almost visibly inseparable from the x-axis. Most all of these are going to cross the x-axis, the y-axis at 1. So there's 0, 1, because anything to the 0 power is going to be 1. Now, of course, you're going to have different things going on if you have functions that take away from the overall. 1 gives me a value of 4. 2 gives me a value of 16. And then if I did have 3, 64 would be way up there. So you can kind of imagine how this just jumps up dramatically. I go and I try my best to connect this. And you'll notice that the appearance of an exponential function is really not the same as what you see happening with the quadratic function. The curvature is definitely different. So I have y equals 4 to the x power for my graph. And when I look at this, there's a couple things I want to pay attention to. Will this ever go below the x-axis? Well, imagine this. If I had 4 in my denominator getting squared, then I'd just be getting way, way crazy larger values over here, to where eventually it's going to be like 1 divided by 1 trillion. And 1 divided by 1 trillion approaches 0, but it's still positive. So there's no way that this particular graph will ever cross the x-axis. In fact, I can draw my line to show where it wouldn't go below, because sometimes that line might be up here, and you're going to learn words for that later. But we won't talk. You're going to learn words for that later, but I'm not going to talk about it now. So I'm just kind of planting the seed there. But I can't really draw a limiting line over here, because that's just going to explode towards infinity after a certain point. Now, looking at 1.8, maybe I draw a very faint guideline using my pencil. Now, I say faint because I don't want you to mix this up with some other concept. This line is just me using a strategy to approximate where I think that value is. Now, based on my graph, it looks like if I were to go walking backwards, it's roughly 14. And I don't know, maybe that's good enough. So I'm using my graph, and I'm going to say it is approximately 14. I'm just guessing. Now here's what I want you to do. In your calculator, I want you to take 4 to the power of 1.8 and see what you get. Well, when you end up doing that, you got like 12.12. So if your graph was more accurate, maybe you got closer to 12 and eyeballing it, but mine was further away. So I'm going to erase 14. Go ahead and say it's about 12 and just move on. Graph y is equal to 7 to the power of x. Make this an OYO problem. And guess at the value of 7 1/10. And then you can use a calculator to control that value, to confirm that. Both of those previous two examples were where we had values greater than 1 in the base of our exponent. And similar to the last one, let's go ahead and set it up with 3 columns with the y value on the far right, and then 1/2 x, 1/2 to the power of x there, as like an in-between semi-optional step. So x is going to be similar to before, -2, -1, 0, 1, 2. But here we'll start at -3, -2, -1, 0, 1, 2. And maybe you'll see why in a moment. Let's see what happens. Here's 1/2 to the power of -3. Now, if I wanted to, I could kind of in-between step this and be like, well, that's going to be 1 to the -3 over 2 to the -3. But 1 to any power is going to just end up being really itself, because negative exponents are not about negative numbers, they're about division. So maybe feel comfortable that this is 1 over 2 to the power of -3, which means that then I can just move it to my positive value. But what this really means is that you can just flip it. Just flip this whole thing upside down, make it positive, so that 1/2 becomes 2 over 1. So this is not 2 to the power of -3 anymore. It's 2 cubed. And these are not a clicking the immediate moment you start them type of thing. So don't feel that way. But I got 1, so don't feel frustrated by it is what I'm saying. So I'm going to have 1/2 to the power of -2, which means I just flip it to be 2 over 1 squared, which is just 4. And 1 over -1 would be the same as -1, and then you can, 1 over 2 to the power of -1 would again get flipped, so that would be just 2 to the first power. Now it's a fraction, 1/2 to the 0 power, it doesn't matter what it is, it's always the same thing. And now this is where it gets easy, 1/2 to the power of 1 is 1/2. 1/2 squared is 1/2 times 1/2, which is 1/4. And if you wanted to check this for reasoning, you could be like, well, half of that is 4, and half of that is 2, and so on, as I went forward. Or you could work your way backwards, doubling it every time. And this would be what we'll later find out is all about decay. We're starting with values that are getting smaller over time when our fractions show up, that are between 0 and 1 as the base of our functions. And looking at this, maybe you're tempted. So I just made a error here. I didn't even use that in-between step. Sorry about that. So change that if you wrote down exactly what I had. So with this graph, we're going to have the x-axis. We're assuming this is going to be symmetrical. Not symmetrical. We're going to assume that we want to have this region the same as that region over there. And just like before, maybe I go back to -2 to +2, +1, -1. Now here, I think We can go up to 10 for this graph. Here's 10. 5, 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to graph -2, +4. -1, +2. 0 is at 1. 1 is at a half. And 2 is at a fourth. Now, sometimes I rotate my page because the movement of that swipe over here gets easier. That's kind of a gross motor movement. And this is going to end up being the graph of y is 1/2 to the power of x. And don't be deceived. You know, this looks like it's flatter than the other one that we made, and it might be. But also look at like how much more narrow the boundaries I made are. You know, here I kind of spread out my numbers more. We got to approximate this. We got to guess about where it would be here. And it looks to me like this is a number that's a little bit more than 5. So maybe I'm going to guess that it's about 6. And in this case, when I do use my calculator, it ended up being 5 7/10. So I think I did a better job for this go around than I did the last one. Here we go. You got some new things to try to find out on your own. Make this an OYO problem. And see me if you need any coaching from it. But there's something new going on over here. So graph that and punch it into Wolfram Alpha and see what you think.